So welcome back. We are now going to look at data modeling. So before I move over to this, I would like to have some sort of summary of what we have learned so far, but on a very high level, from basically both HDFS and HBase. So we have this technology stack that we've discovered. I have 10 lessons on the high level that I would like to share. The first lesson is learning from the past. In the case of HDFS, HBase, so big data, what we've learned is that even though we are trying to rebuild something that is an alternative to relational database management systems like PostgreSQL, we still keep the idea of data independence. The idea that we still have tables, for example, in HBase, we will see that we also will have programming languages and so on, so the same kind of stack. So learning from the past is absolutely fundamental. And an example of when this failed, that we didn't use the opportunities of what our ancestors learned, is between XML and JSON. So what happened is that for reasons probably due to matters of taste or preferences that are not technical, at the beginning of JSON, there was this idea of we don't want XML, it's too complex. And so JSON was developed a little bit independently, the ecosystem. And what happened over time is that in the end, we noticed that after all, we need a schema for JSON. We will see that shortly. We discovered that we also need pointers in JSON. We discovered that we also need a way to navigate JSON. We discovered that we also need a way to query JSON. So all these things that we thought we needed to throw away together with XML, in the end, it was noticed that they were also needed in JSON. And so what happened, if I look back, is that because of that, we probably lost 10 years of development of JSON. That JSON now is in a state with 10 years of delay compared to what it would have been if from the beginning, we would have gotten all the lessons for XML and directly port them into JSON. So this is one example where it's really important to learn from the past because people did mistakes, people made design decisions, and by looking at what they did and trying to take over, you can actually gain a lot of time and speed up and accelerate the developments. The second lesson is to keep the design simple. So the idea here, if you look at object storage, key value model, we have bucket IDs and object IDs that identifies an object. You can get it, put it, delete it, very simple. So this is actually very useful to do that. It's also the spirit of data independence, right? That the API that you expose is very, very simple. And then you focus on the physical implementation, but in a way that's completely hidden from the rest. But keeping the design simple is really something that becomes increasingly important when you start having very large scales. The third lesson is to modularize the architecture. So as a computer scientist, it's not very surprising because we all know, especially, for example, in object-oriented orientation, we know that all these elegant code makes programs better. And so with modularity, we can reuse things. We can also have an overview of things in a way that our little human brains actually understand, because if we try to build everything as a single block, a human would not be able to understand it anymore. So this is also why we have to modularize. So this is why we have the storage, the syntax, the validation, the query languages, and so on, all at different levels, and we build on top of each other. As an example, we have the hard drives connected to computers with an operating system, let's say Linux, connected with network cables to each other in a data center, on top of which you have HDFS, on top of which you have HBase, and on top of which you can even have further layers. Imagine how simpler it is to have designed it in this way with implementing Linux independently of HBase and HDFS, as opposed to trying to directly build as a single block the whole thing as a single code base. That would be a nightmare for any human. So this is why modularizing is very important. A fourth aspect is in order to scale, to have something homogeneous at very, very large scale, meaning that if you look at HDFS from very, very, very far away, you just see files and directories organized in blocks. If you look at object storage or S3 from very far away, you just see objects associated with keys. If you look at HBase from very far away, you just see row IDs and column families and column names with values in there. So it's all homogeneous. But what happens is that if you zoom in and look at one particular object or one particular cell in an HBase table, it will be different from its neighbors. And this is heterogeneity in the small. It's the idea that when you have in HBase plenty of XML documents or plenty of JSON documents in the same column, they don't even have to have the same schema or look alike. You can have a whole diversity of patterns in there, and that is supported by these systems. The same in S3. You can put whatever you want in objects. You can put data sets, files, pictures, it doesn't matter, right? This is absolutely anything. And so you have this contrast on the very high level homogeneity in terms of the design, like a key value model and so on, and or blocks in HDFS, just plenty of blocks. And at the low level in the details, the diversity of what you're actually storing. And it is the contrast between the two that makes, that gives flexibility to the very large scales. Then you have lesson number 6, which is that's data independence. We need to abstract a logical model independently of the physical implementation. It means that when you look at relational tables, you shouldn't care about how the bits are stored on the disk. You just have rows and columns. When you look at HDFS, you shouldn't have to care about how the blocks are actually stored on the disk. You just have blocks, right, on the physical disks. You just have logical blocks, HDFS blocks. You have a logical hierarchy of directories and files. And this is abstracted away from the details with which the data nodes are handling that all, because the data nodes are just doing it behind the scenes in a hidden way. The same goes with HBase, right? You expose HBase with column families and the row IDs independently of HDFS. So when you actually deal with HBase, you don't care about HDFS anymore. And here it's interesting because HDFS that we looked at as a logical layer the week before suddenly becomes a physical layer compared to HBase. Right, so it's all relative to each other. And maybe on top of HBase, HBase can be the physical layer of something else on top of HBase. So this is absolutely fundamental to keep your sanity, to have clean APIs in between the layers. Something else that we saw that is absolutely everywhere is the idea of building partitions of the data, sharding the data. We did it with HDFS, because we have these 128 megabyte blocks. We did it with HBase, because we partitioned by regions and we partitioned by column families. So this is called sharding. Sharding is going to be really all over the place. It's so all over the place that we have plenty of names for the shard. So shard, block, split, partition, there's many of them. We don't only shard, so this is basically the partitioning. We also replicate the shards that are here. So not only do we cut it into these chunks, but we store each chunk multiple times. So in HDFS, the default is 3, even though you can adjust that. And then you spread all of these chunks all over machines. So the way that it feels on a very high level, imagine that now you have all these data sets that are sharded like this into these smaller chunks that are like 100 megabytes. And then you can store these chunks multiple times. Then imagine just like you pour water into a glass and you have all the molecules of water that just spread in space, then imagine that on a cluster, you have millions of these blocks, millions of the HDFS blocks that are just spread all over the cluster. And having a granularity such that there are several thousands of these on every machine allows you to nicely and smoothly spread it all over a cluster, right? So we'll come back to that when we talk about performance. Lesson number 9 is that we don't want bigger machines, or not actually enormous machines. We just want a lot of machines. So now you have the order of magnitude. In one data center, you're looking at 10,000 machines, maybe all the way to several dozens of thousands of machines, maybe to 100,000. And then if you have multiple data centers, then millions or tens of millions or hundreds of millions of machines, right? So a lot of cheap hardware, that is the key to do it all. And basically, all of these shards that you replicate, you spread them all over this cheap hardware that you've bought, right? On the very high level, this is what's happening. And finally, we batch process, and that's actually what we've seen with the flushing and the compaction in HBase. The idea of batch processing is that instead of every time that a user creates a new cell in HBase, writing it to disk, that would be very inefficient because every time we do that, we'd have a latency that would be very slow. Instead, we accumulate the key values in memory until there is enough. We call that a batch. And then we write down that batch when we flush to HDFS. That is batch processing when we do that. All right. So this is called batch processing. And we'll also see that in MapReduce and in Spark. Okay. So where are we? So you see, we're making progress in this stack. So in the past few weeks, we've looked at storage with HDFS and S3 and key value stores. We've looked at encoding, tiny little bits, and we've looked at syntax with XML, JSON, YAML, also a little bit. So this is when we have the data as text, human readable. And today, we are going to look at data models. More precisely, we will focus on 3 data models, like the data models for XML and JSON, knowing that the data models for tables, you've seen them before in the relational database classes, right? But of course, I will connect these things together. All right. So what is the connection between a syntax and a data model? Well, I take the example of CSV, because this is the one that's very intuitive. When you have a CSV file, it's text. Normally, if you look at this as a human with a bit of abstraction efforts, you should see this, right? This is just some text using the commas to separate the cells and the new lines to separate the rows. But what I would like you to see is that if you look at a CSV file, you should see a table, and in your mind, you should actually see that. Because that's exactly what happens when you open a file like that in a spreadsheet software, then you should get something that is actually abstracted away as a table in this way. And basically what I would like for you after the lecture to be able to do is that when you look at XML or JSON, you will also see trees, just like you see tables for CSV. This is my goal, okay? So we have a physical view that is the syntax, so basically the text, and the logical view that is the abstraction of that physical view, where we have a relational table. So now, let's do it for JSON first, because it's the easiest. So if you remember what I told you about JSON and the syntax, there are 6 building blocks, right? Strings, Booleans, numbers, nulls, objects, and arrays, just these 6. So these are, I presented them as syntactic building blocks 2 weeks ago. I showed you what they look like and how objects use these curly braces and arrays use the square brackets. But what I would like for you to be able to do is to see a tree here. So my first question to you, just to get an impression in the room and also over Zoom, who here sees a tree? Okay, on Zoom? Who sees a tree? See quite a few people, right? Okay. Who doesn't see a tree yet? Okay, you will see it. So in the second hour, I will show you how you actually can build a tree out of that. My goal is that this becomes an instinct for you, that as soon as you look at this, you cannot unsee it, basically. You will always see a tree spontaneously because this is in the end what it is. XML and JSON are trees. And we'll see that it's a denormalized form of relational tables. Which brings us to the break. I was just making sure that it doesn't ring in the middle of a sentence. So I'll see you in 15 minutes, and I'll continue to drive you to seeing XML and JSON as trees. Thank you.